Imagine driving a car beneath the ocean, with millions of tons of seawater pressing down above your head. There are no waves to see, no sunlight shining through the water, and no escape to the surface. Surrounding you is nothing but reinforced concrete, solid rock, advanced engineering, and one of humanity's greatest construction achievements. Every day, millions of people travel through underwater tunnels without giving much thought to the incredible technology protecting them. Yet creating a tunnel beneath the sea is one of the most dangerous and technically demanding engineering challenges ever attempted. Unlike bridges, which rise above the water where problems can be seen and repaired, underwater tunnels exist in a hidden world where every mistake could have catastrophic consequences. Engineers are forced to battle enormous water pressure, unstable geology, limited working space, flooding risks, toxic gases, and the constant possibility of structural failure. It is an environment where there is almost no room for error. For centuries, oceans have separated civilizations. They protected nations, encouraged trade, but also created enormous barriers to transportation. Ships were the only practical solution for crossing large bodies of water. Ferries carried millions of passengers every year, but they depended heavily on weather conditions. Storms, strong winds, rough seas, and dense fog could stop transportation for hours or even days. As populations grew and economies expanded, countries began searching for faster, safer, and more reliable ways to connect people and goods across the sea. Building longer bridges seemed like an obvious solution, but not every location made that possible. Deep water, busy shipping lanes, powerful ocean currents, and extreme weather often made bridge construction either technically impossible or financially unrealistic. That is when engineers began considering an idea that once sounded almost unbelievable. Instead of going over the ocean, why not go beneath it? At first, the concept appeared impossible. How could anyone safely excavate through rock buried beneath the seabed while preventing billions of liters of seawater from rushing into the tunnel? How could workers survive in such an environment? And even if construction were possible, could the finished tunnel remain safe for generations? These questions challenged some of the greatest engineering minds in history. For decades, many believed the risks were simply too great. But engineering has always been driven by people willing to challenge what others considered impossible. As technology advanced, new surveying equipment allowed engineers to map the ocean floor with incredible accuracy. Powerful tunnel boring machines capable of cutting through solid rock were developed. Stronger concrete, waterproof ceiling systems, sophisticated ventilation technology, and real-time monitoring systems gradually turned an impossible dream into a realistic engineering objective. One breakthrough after another slowly removed the obstacles that had once stopped previous generations. The result was a new era of infrastructure unlike anything the world had seen before. Massive underwater tunnels began connecting islands to the mainland, shortening journeys that once required hours of travel by ferry into simple drives, lasting only minutes. International trade became more efficient. Emergency services gained faster access to isolated regions. Entire economies benefited from permanent transportation links that operated regardless of weather conditions. Some underwater tunnels now stretch for tens of kilometers beneath seas and channels, carrying trains, cars, and millions of passengers every year with extraordinary safety. Yet these incredible structures remain largely invisible to the public. Unlike towering bridges or soaring skyscrapers, underwater tunnels hide beneath the seabed, quietly performing one of the most complex engineering tasks ever achieved. Behind every kilometer of tunnel lies years of geological surveys, thousands of engineers, millions of tons of excavated rock, gigantic tunnel boring machines, precision-built concrete segments, and safety systems designed to protect human lives every second of every day. Every successful underwater tunnel represents decades of planning, billions of dollars in investment, and engineering solutions developed specifically to overcome one of nature's most unforgiving environments. Today, engineers are pushing these limits even further. New underwater tunnels are becoming longer, deeper, and more technologically advanced than ever before. Some projects aim to connect entire countries beneath busy shipping routes, while others are exploring revolutionary concepts that could redefine transportation for future generations. But before any of these extraordinary projects can become reality, engineers must first answer one critical question. How do you actually build a tunnel beneath the ocean without allowing the sea to destroy everything? That remarkable story begins long before the first machine starts digging, with an extraordinary search for the safest path beneath the seabed. Long before the first tunnel boring machine begins cutting through rock, engineers face perhaps the most important decision of the entire project. They must determine exactly where the tunnel should be built. Choosing the wrong route could increase construction costs by billions of dollars, or create engineering problems that might never be fully solved. Unlike roads built across open land, an underwater tunnel cannot simply change direction if unexpected conditions are discovered during construction. Every kilometer must be carefully planned years in advance, making the investigation phase one of the most critical parts of the entire project. The process begins with an extensive survey of the seabed. Specialized research vessels equipped with multi-beam sonar systems slowly travel across the proposed route, sending thousands of sound waves toward the ocean floor every second. These signals bounce back to the ship, creating an incredibly detailed three-dimensional map of the seabed. Engineers study underwater mountains, deep trenches, rock formations, and hidden obstacles that could interfere with construction. But mapping the surface alone is not enough. The greatest challenges are often hidden hundreds of meters below the seabed. To understand what lies beneath, drilling platforms collect long cylindrical rock samples known as core samples. These samples reveal the strength, composition, and stability of the underground geology. Engineers examine every layer, searching for solid granite, fractured rock, loose sediment, underground water pockets, and geological fault zones. Even a small section of unstable ground can require major changes to the tunnel's alignment. Every discovery influences thousands of engineering decisions that will follow. Ocean pressure creates another enormous challenge. The deeper the tunnel is located beneath the seabed, the greater the pressure acting on the surrounding rock and tunnel lining. Engineers must calculate these forces with extraordinary accuracy because the finished structure will need to withstand constant pressure every second for more than a century. Sophisticated computer simulations combine geological information, water pressure, seismic activity, and rock behavior to predict exactly how the tunnel will perform long before excavation begins. Every possible risk is analyzed. What happens if groundwater suddenly enters the excavation? What if unexpected fractures appear inside the rock? What if an earthquake occurs decades after construction is complete? Modern engineering attempts to answer these questions before a single meter of tunnel has been excavated. Safety is considered at every stage of the design process. Engineers determine the maximum distance between emergency exits, ventilation stations, escape passages, and maintenance areas. Powerful ventilation systems must continuously provide fresh air while removing vehicle exhaust, smoke, and heat generated inside the tunnel. Emergency cross passages are designed to allow people to quickly escape into a safe area if an accident occurs. Fire detection systems, surveillance cameras, communication networks, and intelligent traffic management systems are integrated into the design long before construction begins. Unlike ordinary road tunnels, underwater tunnels require multiple layers of protection because evacuation options are far more limited beneath the ocean. The route itself is rarely chosen as the shortest distance between 2 points. Engineers often select a slightly longer alignment if it passes through stronger and more stable rock. Solid bedrock provides a much safer environment for excavation than soft sediment or fractured geological formations. In many cases, avoiding unstable ground can reduce long-term maintenance costs and significantly improve structural safety. Every additional kilometer of tunneling represents enormous expense, but building through poor geology could prove far more costly over the lifetime of the project. Environmental considerations also play an increasingly important role. Construction activities must minimize disruption to marine ecosystems, fisheries, shipping lanes, and coastal communities. Detailed environmental impact assessments evaluate how excavation, dredging, underwater blasting, and construction traffic may affect surrounding habitats. Engineers work closely with environmental scientists to develop solutions that protect both the project and the natural environment. Modern underwater tunnels are no longer designed solely for engineering performance. They are also expected to meet strict environmental standards while supporting long-term sustainability. Once years of surveys, drilling, laboratory testing, computer simulations, and environmental studies have finally been completed, engineers reach the moment they have been working toward from the very beginning. The final alignment is approved. Every curve, every gradient, every emergency exit, every ventilation shaft, and every construction access point has been carefully planned. Only now can one of the most extraordinary machines ever built by humanity begin its work. Deep beneath the ocean, a giant tunnel boring machine will soon begin cutting through solid rock meter by meter, transforming an impossible dream into reality. In the next chapter, we'll step inside these incredible machines and discover how they excavate some of the longest underwater tunnels ever constructed. Once the route has been approved and every geological survey completed, the most extraordinary phase of the project can finally begin. Deep below the ocean floor, one of the most powerful construction machines ever created starts moving forward. It is called a tunnel boring machine, or simply a TBM. These incredible machines are not just drills. They are complete underground factories capable of excavating rock, removing debris, installing tunnel walls, monitoring geological conditions, and building a finished tunnel simultaneously. Some TBMs are longer than 2 football fields and weigh several thousand tons. Their rotating cutter heads measure more than 15 meters in diameter and are equipped with dozens of massive disc cutters capable of crushing some of the hardest rock found on Earth. As the enormous cutter head slowly rotates, each steel cutter presses against the rock with tremendous force, breaking it into smaller fragments through pure mechanical pressure. Every rotation advances the machine only a few centimeters, but hour after hour and day after day, those few centimeters eventually become kilometers of tunnel hidden beneath the seabed. Behind the rotating cutter head lies one of the most sophisticated engineering systems ever assembled. Powerful hydraulic cylinders push the entire machine forward, using the concrete tunnel rings already installed behind it as support. At the same time, conveyor belts continuously transport thousands of tons of broken rock back through the tunnel, where it is loaded onto trains or trucks and removed from the construction site. Every movement is carefully synchronized. If excavation moves too quickly, the tunnel lining may not be installed in time. If it moves too slowly, the entire project schedule can fall behind by months. Maintaining this delicate balance requires constant monitoring by engineers working around the clock. Perhaps the most remarkable feature of a modern TBM is that it builds the tunnel as it excavates. Immediately behind the cutter head, giant robotic arms lift enormous precast concrete segments into position with incredible precision. These curved segments fit together like pieces of a giant puzzle, forming a complete circular ring around the newly excavated tunnel. High-strength bolts lock each segment into place, while specialized rubber gaskets create watertight seals capable of preventing seawater from entering the tunnel even under extreme pressure. Once a complete ring has been installed, the hydraulic cylinders push against this new structure, allowing the machine to advance once again. This cycle repeats thousands of times until the tunnel is complete. Between the surrounding rock and the newly installed concrete lining, engineers inject specialized grout under high pressure. This grout fills every small gap, preventing ground movement while creating additional support for the tunnel structure. Without this process, tiny voids could eventually allow groundwater to accumulate, increasing pressure on the lining or causing long-term settlement. Although passengers driving through the finished tunnel will never see this hidden layer of engineering, it plays a critical role in ensuring the tunnel remains stable for generations. Navigation beneath the ocean requires extraordinary precision. Unlike surface construction, engineers cannot simply look outside to verify their position. Instead, advanced laser guidance systems constantly monitor the exact location of the TBM. Every few meters, computers compare the machine's actual position with the planned alignment. Even a deviation of only a few millimeters is detected immediately and corrected before it becomes a larger problem. On projects where 2 TBMs begin excavating from opposite sides of the sea, this precision becomes even more important. After years of excavation, the 2 tunnels must meet almost perfectly in the middle. Modern surveying technology has made such incredible accuracy possible, allowing machines operating kilometers apart to connect with astonishing precision. Working conditions inside a TBM are unlike almost any other construction environment. Crews operate in confined underground spaces 24 hours a day. Powerful ventilation systems constantly supply fresh air while removing dust, heat, and exhaust gases. Pumps operate continuously to remove groundwater entering the excavation. Electrical systems provide power for hundreds of motors, hydraulic pumps, lighting systems, and computer controls. Every component must function reliably because a major mechanical failure beneath the ocean can take weeks to repair. Maintenance crews inspect cutters, hydraulic systems, bearings, conveyor belts, and electrical equipment constantly, replacing worn components before they fail. As the machine progresses deeper beneath the sea, geological conditions often change unexpectedly, Engineers may encounter harder rock, fractured fault zones, underground water pockets, or sections of unstable ground that were impossible to detect during earlier surveys. When this happens, excavation speed is reduced while additional reinforcement measures are installed. Specialized drilling equipment injects cement or chemical grouts into weak ground ahead of the cutter head, strengthening the surrounding rock before excavation continues. Every unexpected challenge requires rapid decisions from experienced engineers because delays can quickly affect the entire construction schedule. After months or even years of continuous excavation, the tunnel finally reaches its destination. But despite the extraordinary achievement of boring a passage beneath the ocean, the project is still far from complete. Electrical systems, ventilation equipment, lighting, drainage, communications, fire protection, emergency exits, railway tracks, or road surfaces must all be installed before the tunnel can safely open to the public. Yet even after construction is finished, the greatest challenge remains. Every day, millions of tons of seawater continue pressing against the tunnel, testing every concrete segment, every waterproof seal, and every engineering decision made during construction. In the next chapter, we'll discover the hidden dangers that threaten underwater tunnels and the incredible technologies engineers use to keep them safe every second of every day. Completing an underwater tunnel does not mean the engineering challenges are over. In many ways, they are only just beginning. Unlike bridges that can be inspected from the outside, underwater tunnels spend their entire lives hidden beneath millions of tons of seawater. Every second of every day, enormous pressure pushes against the tunnel lining, attempting to force water through the smallest crack or weakness. Although passengers experience nothing more than a normal drive or train journey, engineers know that beneath the smooth concrete walls lies one of the harshest operating environments ever created by nature. Keeping these tunnels safe requires constant monitoring, advanced technology, and decades of engineering expertise. One of the greatest threats is water infiltration. Even the smallest opening can allow seawater to enter under extremely high pressure. Over time, water can damage electrical equipment, weaken reinforcement, accelerate corrosion, and create dangerous operating conditions. To prevent this, every concrete segment is manufactured with extraordinary precision and connected using high-performance waterproof gaskets, specifically designed to withstand decades of continuous pressure. Multiple drainage systems hidden behind the tunnel lining collect any small amount of seepage before it can reach the roadway or railway. Powerful pumps operate continuously, removing water 24 hours a day. Most travelers never realize that an entire hidden drainage network is working beneath their feet throughout every journey. Geological instability presents another major challenge. Even after years of surveys, engineers can never predict every condition hidden beneath the seabed. Rock formations naturally shift over time. Tiny fractures may slowly expand under pressure. Groundwater conditions change. In some regions, underwater fault lines remain active, creating the possibility of earthquakes beneath the ocean floor. Modern underwater tunnels are therefore designed with flexible joints and reinforced structural systems capable of absorbing small movements without losing their structural integrity. Thousands of monitoring sensors embedded throughout the tunnel continuously measure deformation, vibration, pressure, temperature, and structural stress. These sensors send real-time information to centralized control centers, where engineers monitor every section of the tunnel 24 hours a day. If even the slightest abnormal movement is detected, maintenance teams can investigate long before it becomes a serious problem. Fire is another danger that engineers take extremely seriously. Inside an underwater tunnel, smoke is often more dangerous than flames themselves. In a confined underground environment, smoke can spread rapidly, reducing visibility and making evacuation extremely difficult. To address this risk, powerful ventilation systems are installed throughout the tunnel. Massive jet fans mounted along the ceiling can quickly control airflow, directing smoke away from evacuation routes and allowing emergency services to reach the affected area more safely. Sophisticated fire detection systems use heat sensors, smoke detectors, thermal cameras, and automated monitoring software to identify incidents within seconds. Some tunnels even include automatic fire suppression systems designed to limit damage while emergency crews respond. Vehicle accidents also require careful planning. Modern underwater tunnels include emergency telephones, surveillance cameras, variable message signs, emergency lighting, escape passages, fire-resistant shelters, and clearly marked evacuation routes. Cross passages connecting parallel tunnels allow people to quickly move into a protected escape corridor if necessary. Every aspect of emergency response is carefully planned long before the tunnel opens. Engineers regularly conduct emergency drills involving firefighters, police, medical teams, and tunnel operators to ensure that every organization can respond immediately if an incident occurs. Air quality must also be carefully controlled. Thousands of vehicles passing through a tunnel produce exhaust gases, heat, and fine particles that would quickly accumulate without proper ventilation. Powerful ventilation systems constantly circulate fresh air while removing harmful gases and maintaining safe oxygen levels. Advanced air quality sensors continuously measure carbon monoxide, nitrogen oxides, visibility, temperature, and humidity. Intelligent control systems automatically adjust fan speeds depending on traffic volume, weather conditions, and air quality measurements, ensuring a safe environment for every traveler. Security has become increasingly important in modern infrastructure. Underwater tunnels represent critical transportation links connecting cities, regions, and even entire countries. Any disruption could have significant economic consequences. As a result, modern tunnels use extensive security systems including high-definition surveillance cameras, motion detection, license plate recognition, access control, cybersecurity protection, and artificial intelligence capable of identifying unusual activity in real time. Many control centers now use AI-assisted software to analyze thousands of camera feeds simultaneously, allowing operators to respond far more quickly than would be possible through manual monitoring alone. Perhaps the most remarkable aspect of these engineering masterpieces is that most travelers never notice the extraordinary technology surrounding them. They simply drive through a well-lit tunnel, unaware of the thousands of sensors, pumps, ventilation fans, emergency systems, communication networks, and structural monitoring devices working silently behind the walls. Every second, these hidden systems protect millions of lives while ensuring one of the world's most challenging engineering environments remains completely safe. Yet engineering never stands still. Even today's underwater tunnels are only the beginning. Around the world, engineers are already developing smarter, longer, and more advanced tunnels using artificial intelligence, robotics, digital twins, and next-generation construction technologies. In the next chapter, we'll explore how these innovations are transforming the future of underwater tunnel engineering and bringing humanity closer to projects that once seemed impossible. For more than a century, underwater tunnels have connected islands, linked nations, and transformed transportation across the world. But the tunnels being built today are only the beginning. Engineers are now entering a new era where artificial intelligence, robotics, advanced materials, and digital engineering are completely changing how these extraordinary structures are designed, built, and maintained. The next generation of underwater tunnels will not simply carry people beneath the ocean. They will become intelligent infrastructure capable of monitoring their own condition, predicting maintenance needs, communicating with traffic management systems, and adapting to changing environmental conditions in real time. What once required thousands of manual inspections can now be accomplished by networks of sensors and powerful computer systems working continuously behind the scenes. Artificial intelligence is already becoming one of the most valuable tools in tunnel engineering. Modern underwater tunnels contain thousands of sensors embedded throughout the concrete lining, ventilation systems, electrical equipment, drainage networks, and structural supports. Every second, these sensors collect enormous amounts of information about temperature, humidity, vibration, structural movement, water pressure, air quality, traffic flow, and equipment performance. Instead of relying solely on engineers to manually analyze this data, AI systems continuously search for patterns that could indicate developing problems. A slight increase in vibration may suggest bearing wear inside a ventilation fan. A tiny change in structural movement could indicate ground settlement. Small variations in water pressure may reveal the earliest signs of seepage long before it becomes visible. By identifying these changes early, engineers can perform maintenance before failures occur, reducing costs while significantly improving safety. Digital twin technology is creating another revolution in underground engineering. Every major underwater tunnel can now have a complete virtual copy existing inside powerful computer systems. This digital twin is constantly updated using real-time information collected from thousands of sensors throughout the tunnel. Engineers can simulate traffic accidents, flooding scenarios, equipment failures, earthquakes, fires, and extreme weather events without affecting the real tunnel. They can test new ventilation strategies, evaluate emergency evacuation procedures, and optimize maintenance schedules before making changes in the real world. Instead of reacting to problems after they occur, digital twins allow engineers to predict future conditions with remarkable accuracy. Robotics is also transforming tunnel maintenance. In the past, inspecting an underwater tunnel often required maintenance crews to close traffic lanes, enter confined spaces, or work in hazardous environments for long periods. Today, autonomous inspection robots equipped with high-resolution cameras, laser scanners, ultrasonic sensors, and thermal imaging systems can travel through tunnels independently, identifying cracks, corrosion, water leaks, damaged concrete, and equipment failures with incredible precision. Some robots can even climb tunnel walls or inspect drainage systems that would be extremely difficult for humans to access safely. Underwater remotely operated vehicles are now being used to inspect submerged tunnel entrances and underwater structures without requiring divers, reducing both risk and inspection time. Construction technology continues evolving just as rapidly. The next generation of tunnel boring machines is becoming increasingly automated. Advanced navigation systems allow machines to maintain millimeter-level accuracy while excavating through complex geological conditions. Artificial intelligence assists operators by analyzing cutter wear, predicting ground conditions ahead of the machine, and optimizing excavation speed to maximize both safety and efficiency. Future TBMs may eventually perform many construction tasks with minimal human intervention, dramatically reducing project duration while improving construction quality. Engineers are also exploring entirely new tunnel concepts. One of the most ambitious ideas currently under development is the floating underwater tunnel. Instead of resting beneath the seabed, these tunnels would be suspended underwater using enormous buoyancy systems anchored to the ocean floor. Norway, with its deep fjords and challenging coastline, has been studying this concept for years. If successfully developed, floating tunnels could eliminate the need for extremely deep excavation while opening entirely new possibilities for transportation across large bodies of water. Although the concept remains under development, it demonstrates how engineering continues pushing beyond what once seemed possible. Environmental sustainability is becoming equally important. Future underwater tunnels are expected to use lower carbon concrete, recycled construction materials, renewable energy systems, intelligent lighting, and highly efficient ventilation technologies that significantly reduce energy consumption. Construction methods are also being refined to minimize disturbance to marine ecosystems, fisheries, and coastal habitats. Rather than focusing only on technical performance, engineers are increasingly designing infrastructure that balances transportation efficiency with long-term environmental responsibility. Perhaps the most exciting possibility is the integration of underwater tunnels into future smart transportation networks. Autonomous vehicles, intelligent traffic control systems, real-time navigation, and connected infrastructure may eventually allow traffic to move through tunnels more efficiently and more safely than ever before. Sensors embedded throughout the tunnel could communicate directly with vehicles, warning drivers about hazards ahead, adjusting speed limits automatically, and optimizing traffic flow to reduce congestion and improve emergency response times. Every generation of engineers has expanded the limits of what humanity believed possible. The first underwater tunnels proved that people could safely travel beneath rivers. Later generations crossed seas and connected entire nations. The engineers of today are building infrastructure that not only survives beneath the ocean but also thinks, monitors itself, and continuously adapts to changing conditions. Yet despite all these technological advances, the greatest achievement of underwater tunnels may not be the concrete, steel, or machines used to build them. It is the confidence they give humanity to continue solving problems that once seemed impossible. In our final chapter, we'll look back at how underwater tunnels have changed the world and why these hidden engineering masterpieces may become one of the defining achievements of modern civilization. As we reach the end of our journey, one thing becomes absolutely clear. Underwater tunnels are far more than transportation infrastructure. They represent some of the greatest engineering achievements in human history. Hidden beneath oceans, rivers, and straits, These remarkable structures quietly connect cities, countries, and millions of people every single day. Most travelers never stop to think about the incredible engineering surrounding them. They simply drive through a brightly lit tunnel, unaware that millions of tons of seawater are pressing down only a short distance above their heads. Behind every successful journey lies decades of scientific research, thousands of engineers, millions of working hours, and countless technological innovations that have transformed what was once considered impossible into an everyday reality. Every tunnel tells a story of determination, precision, and human ambition. The impact of underwater tunnels extends far beyond reducing travel time. They strengthen economies by creating faster transportation routes for people and goods. They improve emergency response by providing reliable access regardless of weather conditions. They reduce dependence on ferries that can be delayed by storms or rough seas. Businesses gain more efficient supply chains, tourism expands as destinations become easier to reach, and communities separated for centuries by water suddenly become permanently connected. In many cases, the construction of a single underwater tunnel changes the economic future of an entire region. What was once a difficult journey lasting hours can become a simple drive measured in minutes. These extraordinary projects also demonstrate how engineering continues to evolve. Every new underwater tunnel is safer, smarter, and more efficient than the one built before it. Stronger construction materials, more powerful tunnel boring machines, artificial intelligence, digital twins, autonomous inspection robots, and advanced monitoring systems have transformed tunnel construction into one of the most technologically advanced fields in civil engineering. The lessons learned from one project are applied to the next, allowing engineers to construct longer tunnels, overcome greater water depths, and solve increasingly complex geological challenges. Every completed tunnel becomes both an achievement and a classroom for the engineers who will design the next generation of megaprojects. Yet despite all the technology involved, underwater tunnels ultimately represent something much greater than engineering alone. They demonstrate humanity's ability to overcome natural barriers through knowledge, innovation, and cooperation. Oceans that once divided civilizations now connect them. Mountains that once blocked transportation are crossed through underground passages. Distances that once isolated entire communities have been dramatically reduced through engineering solutions that previous generations could scarcely imagine. Throughout history, every great civilization has been defined by the infrastructure it built. Roman roads connected an empire. Great bridges united cities. Railways transformed continents. Today, underwater tunnels continue that tradition by creating invisible connections beneath the sea that support modern civilization every hour of every day. Looking toward the future, engineers are already planning projects even more ambitious than those we see today. Floating underwater tunnels suspended beneath the ocean surface, longer cross-sea connections linking entire nations, autonomous tunnel construction powered by artificial intelligence, and fully integrated smart transportation systems are moving from concept to reality. What seems extraordinary today may become completely ordinary for future generations. The history of engineering has always followed the same pattern. Yesterday's impossible dream becomes today's engineering masterpiece and tomorrow's everyday infrastructure. Underwater tunnels are living proof that human imagination has no fixed limit when supported by science, determination, and continuous innovation. Perhaps the greatest lesson these hidden engineering marvels teach us is that the most important achievements are not always the ones we can see. Some of humanity's greatest accomplishments exist quietly beneath our feet, performing their task every second without attracting attention. Hidden beneath the ocean, protected by concrete, steel, and extraordinary engineering, these tunnels remind us that true innovation often works silently while changing the world around us. Every kilometer excavated beneath the seabed represents another step forward in humanity's endless pursuit of progress. Every successful project proves that barriers once considered impossible can eventually be overcome through engineering excellence. Thank you for watching Ant Hill's BuildVerse. If you enjoy discovering the world's greatest megaprojects, giant construction machines, groundbreaking engineering, and the incredible technologies shaping our future, make sure to subscribe and join us on our next adventure. From record-breaking bridges and underwater tunnels to massive dams, futuristic cities, and the world's largest construction projects, we'll continue exploring the engineering masterpieces that are transforming our planet. Until next time, keep building your curiosity, Because somewhere in the world, another impossible project is already becoming reality.